Hey guys, in this video we're going to be taking an algebraic approach to finding the inflection points of a given polynomial function and then determining the concavity, whether it's concave up, concave down, and then we'll finish by also looking at the increasing, decreasing along with the concavity. So the first thing that we should just be reminded of here is how to find an inflection point. Remember, an inflection point is where f double prime of x equals 0. So those are the 2 points, or the points where f double prime of x equals 0. We're just going to take the second derivative of the function, set it equal to 0, and then solve for it. So let's go ahead and do that with this function. F prime of x, 3x squared plus 36x. And then f double prime of x would just be 6x plus 36. So then we set that equal to 0. 6x is negative 36, so x is negative 6. So only one inflection point of this one. That's all that we're asked to find in this particular question. So negative 6. All right, next question we're asked, where is this function concave up? So we're going to start it the same way. We're going to find the inflection points, and then we're going to set up a little table here to determine where it's concave up, concave down. So first up, first derivative, again, it's going to give us, looks like 15 over 20, x to the fourth, minus 21x squared. And then f double prime of x, this turns into 3/4. So when that 4 multiplies down, it just becomes 3, x to the third, minus 42x, equal to 0. We'll then have to do a little factoring here. Let's pull out a 3 and an x. And then we're left with x squared minus 14 equals 0. So then we have 3x equal to 0, x squared minus 14 equal to 0. So this one, just to get to x equals 0, our first inflection point, this one is going to be x squared equals 14. So x equals plus and minus radical 14. Make sure you do not forget that plus and minus portion of it. And we'll just leave it as radical 14. Don't make it a decimal or anything at this point. Just leave it as is. So we got 3 inflection points, x equals 0, negative radical 14, and positive radical 14. So let's go ahead and make a little chart here. We're going to set this up in a similar way that we did with the intervals of increasing, decreasing. And then we'll tie that all together in the last set of problems. So we're going to start just by setting up intervals. So our first interval is going to be from negative infinity up to our first inflection point. So the first one that we encounter on the negative direction would be negative square root of 14. We then go from negative square root of 14 to 0, our next inflection point. We go from 0 to our next inflection point, which is positive square root of 14, and then positive square root of 14 to positive infinity. Then we're going to do some test points. So we're going to plug these test points into f double prime. So we need to plug f double prime of, you get it right, x or b or whatever. So we need to plug in numbers that would fit in there. So square root of 14, well, that's somewhere between 3 and 4 because square root of 9 is 3, square root of 16 is 4. So it's probably like, negative 3.8 or something like that. So let's just plug in negative 4. And we just want to see if that is a positive or negative, and actually erase the derivative. So let me pull that back up here real quick. That was 3x to the third minus 42x. All right, that was f double prime of x. So we're going to plug them into that. You could, I would just plug this into your y equals so you don't make a mistake. Plug it into y1, 3x to the third minus 42x, and then just do the table. So if we plug in -4, we get -24. With a little more space. Okay, next I'm going to do f double prime of, let's just say, -1. That's a positive 39. Let's do f double prime of just positive 1 will work. It's on the next interval. It's -39. And let's just do 4 for the last one. F double prime of 4. And that is positive 24. All right, so we had a negative, positive, negative, positive. And then, so in the last column, we're just going to write the concavity. Since this one was a negative, when we plugged in the second derivative, that's concave down. This one's a positive, so it's concave up. Negative, so it's concave down. Positive, so concave up. So there's our 3 intervals of concavity. In this particular question, we are asked where is it concave up. So we're going to type in these 2 intervals, parenthesis, negative, and we'll see the radical symbol. I guess you got to hit this little keyboard here to get the radical symbols to come up. So negative radical 14 to 0, union, positive radical 14 to infinity. And there we go. So you can see here, they did just a little number line type deal. But again, I prefer the table because we're going to end up putting a lot of information on these tables. So see it there. All right. Let's go ahead and do the next one. All right, inflection points. Let's go do another one. Inflection point, concave down. All right, so concave down. So f prime of x first is just going to be 1x to the 4th, and we multiply that down, plus 4x to the 3rd. So f double prime of x, 4x 3rd, plus 12x squared. Set that equal to 0. In this case, we're going to pull out a 4x squared. We're left with x plus 3. So our 2 inflection points would then be 0 and -3. So then let's just think about how we're going to set up our intervals. A little bit easier. Intervals always start from -infinity because these are polynomial functions up to -3. Then from -3 up to our next inflection point, which is 0. And then 0 to positive infinity. We then plug in test points. So f double prime of, so b. So f double prime of, say, -4 for the first one. Again, we're plugging these into our second derivative. So I'm going to plug that second derivative into the y1. Make a table. Plug in -4, we get -64. So it's a negative. F double prime of, say, -1. It's positive 8, positive. And f double prime of positive 1 is still positive 16. All right. So at this one inflection point, it kind of goes to 0, but then it stays as a positive. And we're asked to figure out where it's concave down. So we'd have concavity, down, up, up. So the only interval there would be -infinity to -3. All right, so that's that. Let's go ahead and look at the next section. On this section, we're going to have to determine both the concavity and increasing/decreasing. So I'm actually going to pull up another page here so we got more room. All right, so we're asked to find where it's decreasing in concave up, and got it written over here. So first thing that we're going to want to do, find the first derivative, 4x to the third plus 24x squared plus 36x. And at this point, I'm going to actually just stop here for a second and set this equal to 0 and solve it, because I am going to need critical points, because I'm going to need to figure out where it's increasing or decreasing. So my critical points are going to be where this first derivative equals 0. So with this, it's a trinomial, so let's go ahead and see if we can pull out a greatest common factor. We can pull out a 4 and an x. Then we're left with x squared plus 6x plus 9. So 4x equal to 0. This will be factored into x plus 3 quantity squared. Yeah, x plus 3 times x plus 3. So then we get x equals 0 and x equals -3. So those are my two critical points. Again, this is where the function changes from increasing to decreasing possibilities. Let's go ahead and then find our inflection points. So for that, we need to take a second derivative. That's going to be 12x squared plus 48x plus 36. And then we'll set those that equal to 0. 12x squared plus 48. For that one, we can pull out a 12. We're left with x squared plus 4x plus 9. We can then factor this. Let's see. 3 and is that factorable? Doesn't look like it's factorable to me. Let's see. So we just got 3 and 3 or 1 and 9. Well, that is not going to be factorable. Well, that's fun. All right. So I think we actually need to use the quadratic formula to solve that. Let's go ahead and bust that out. All right. X equals, and if you can't remember it, -b plus or minus the square root of b squared minus 4ac all over 2a. It's weird that they would throw one of these in here, but well. All right. Oh, well, it'd help if I did this right. This is not 9. This is 3. So that didn't make sense. Sorry about that, guys. That shouldn't be 9. That's a 3. Didn't make sense that they would give you a quadratic formula question. All right. Let me correct that. Plus 3. That makes more sense. All right. So then it's x plus 3 and x plus 1. So then our two solutions are just x equals -3 and x equals -1. These are our inflection points. All right, so now we're going to set up one giant table. This is something that, like on a free response question on the AP test, if you had like something like this, drawing the table is a great way to show your evidence for basically how you solved it. Because you do have to prove that you solved it, you have to show your work. So drawing one of these tables is a great way to do that. All right, so we're going to kind of combine our critical points and our inflection points. In a sense, we're going to combine these and split up our intervals accordingly. So first off, we're just going to do intervals. We'll always start with -infinity. And go to our first either critical or inflection point. Now this one actually works out kind of nicely because -3 is both a critical number and an inflection point. So -infinity to -3. That kind of wipes out both of those. We then have -3 up to our next critical number or inflection point, and that's -1. -1 up to our next one, which is 0. And then we don't have any more, so 0 to infinity. All right, so those are intervals. These are all the places where it changes either concavity or increasing, decreasing. Okay. So again, we include all of those. We just sort of order them from least to greatest. So next up, we're going to test them into our first derivative. So we're going to do f prime of b. So we're going to plug in a number on that interval. So f prime of, say, -4. And we plug this into the first derivative. So I'm going to go and pull out my calculator, plug that first derivative into the y equals. Get -16. So it's negative f prime of -2 for the next one. -2 is still negative. And then for this one, f prime of -0.5. Try that. Still negative. F prime of 1, the last one. That is a positive. All right. So what does this say about increasing, decreasing? First one is negative. That tells us our function is decreasing. Negative, decreasing, still decreasing, still decreasing. And then finally it switches to increasing. So that's our first thing. Next up, we need to figure out where this is concave up or concave down. So we're going to be plugging numbers into our second derivative, so f double prime of b. So let's do f double prime of -4. We can use the same numbers, but we do need to change our function in our y equals x squared plus 48x plus 36. All right, first one, -4 is positive 36. F double prime of -2 is -12. F double prime of -0.5 is positive 15. And f double prime of 1 is a positive 96. So then lastly, we can go ahead and write the concavity, whether it's concave up or down. So the first one was a positive, so that means concave up. Negative is down, positive is up, positive is up. All right, so this is a good table that you should know how to make. This table can prove pretty much anything that you need to tell us about the polynomial function. You could theoretically almost sketch a function based off of this as well, because you could also say another thing that you could add to this would be mins and maxes, right? You'd look at where it changes from increasing and decreasing. So actually this one would only have, if you were to add like a little table on here, min max, this is a good thing to add on it as well. There's only one place where it changes from increasing to decreasing or decreasing to increasing. And that is right here, right? So you could say that there's actually it's from decreasing to increasing, right? So that's a relative min that's at 0. And then to get the y coordinate, you would actually plug it into the original function. When you plug it in the original, it actually give you 0. So there's relative min at 0, 0. So you could pretty much sketch the function given all this stuff. All right, but let's answer the question. Decreasing and concave up. So we had a decreasing and up here and a decreasing and up here. So we've got two intervals, -infinity to -3 and -1 to 0. -3 union 1 to 0. Oh, that's not right. Whoops. I think it's -1. 0. Yeah. Whoops. All right, we did it. So I know there's a lot going on in that problem. You can see they actually drew a little sketch of the function here. This is a lot of work, and I realize that it might take you a while, but this is something you really got to know how to do. So do your best there. You can see here on the intervals, first one it's decreasing and up, then it switches to decreasing and down, then it switches to decreasing and up again, and then it switches to increasing and up. So that's how it plays out there. All right, let's do one more of those. And all right, increasing up. Let's go ahead and try that. Pause it. All right, so first thing we need to do is first derivative. F prime of x is 4x to the third minus 24x squared plus 36x. I like to stop here and go ahead and get my critical points. Set this equal to 0. And it looks like we're going to pull out a 4x. We're left with x squared minus 6x plus 9. So then we get 4x equals 0. This factors into x minus 3. Looks like quantity squared. Yep. So then x is 0 is a critical number, and x equals positive 3 will be a critical number as well. These are critical points. If I can spell critical. All right. So then we go ahead and go to the second derivative. 12x squared minus 48x plus 36. And set that equal to 0. We can go ahead and pull out a 12. We're left with x squared minus 4x plus 3 equal to 0. That factors into x minus 1 and x minus 3. So we get x equals 1 and x equals 3. So we end up having an overlap again. That is not always the case, but it just ended up happening in both of these. All right, so we got our inflection points, our critical numbers. So now we can set up our intervals. Again, we got to consider all of these. So our first one's always negative infinity up to our first one, which is going to be, it looks like 0 in this case. 0 to our next one, which is 1. 1 to our next one, which is in both, it's 3. And then 3 to infinity. Once you get the hang of this, it really isn't bad. Just can take a little time. So then let's go ahead and plug in some values. F prime of b. Let's do f prime of -1, and then we'll plug in f prime of 0.5, f prime of 2, and then f prime of 4. So I'm just going to go ahead and set up my table, plugging the first derivative into y1 on my calculator. Plug in -1, I get a negative 64. Plug in 0.5, I get a positive. Plug in 2, I get a positive. Plug in 4, I get a positive. So for increasing, decreasing, we got decreasing, increasing, increasing, increasing. Then we can go ahead and switch to our second derivative. Switch to blue. So f double prime of b, just going to be f. We can probably plug in the same numbers, -1, but you do need to show what you're plugging in. Again, this is all evidence for an AP question to prove basically anything that you want to about this polynomial function. You might even be asked to make one of these charts. All right, so plug in just our new second derivative there, 12x squared into our y1. The numbers are already in there, so it's just going to be random. So it's positive, positive, negative, positive. So we got concavity, up, up, down, down, up, sorry. Again, if we were to identify mins and maxes, the only place there would actually be one where it changes. So it changes from decreasing to increasing. So there would be a relative min again at actually 0, might be 0, 0 again. The original function, I think, would be, yeah, I think it'd be 0, 0 again. Because that's where it changes from decreasing to increasing. We are asked to find increasing and up. So increasing up, increasing up. So 0 to 1 and 3 to infinity. All right, so that is it. Again, this might take you a little time. Just persevere, make sure you're checking your work well. And as always, let me know if you have questions.